Okay, so far we already cover a few steps towards trying to generalize the neural network. As you can see that why I introduced to you with two notation, which is the local error E and the delta, is because you realize that by introduce you with delta, you can see that to find the delta doesn't matter whether the delta is belong to the neuron at the output layer or delta which is belong to the neuron at the hidden layer. You see that to find that delta is similar. There's a common or general equation to calculate that things, means that to find the delta, for example delta 5, then you need to multiply your E5 with your derivative of your activation function here. So this E5 times this one, then you get the delta 5. So same go to any point, doesn't matter is it neuron 3, 4, 5 or 6. So the equation is similar. The ones you find out, the one which is not similar is that the definition of E, or the definition of local error. You can see at the output layer, the E5 and as well as E6, to find or to calculate this value is you must compute by this definition, where you must minus between your actual output Y1 minus your predicted output Y1, and of course you have a minus there to get your E5. Same go to the E6. To find that, you must using this expression, but at the hidden layer to find E3 or E4, then this one you need to find this one, for example E3, then you need to multiply between W35 times your delta 5 plus W36 plus multiplies delta 6 to find E4. The wake for 5 multiply with delta 5 plus W46 times delta 6. So that is how you find E3 and E4, which is not similar as compared to you find when you want to find the E5 and A6. So that is the difference between hidden layer, neuron at the hidden layer, and the neuron at the output layer. The difference is just the definition of E. So meaning that of course in general, that is how the backpropagation is look like. Meaning that the process is that you need to apply the forward pass for the purpose of finding your E. Once you find your E, then to compute the updater, where the updater of every wake there, doesn't matter is it W or is it B, is depend on the gradient of that W or B. To find the gradient of W or B, then you need to pass all the error towards from the right hand side to the left hand side. So that is where you need to apply or to compute the E there, and as well as the delta there, where that is where you can find each and every gradient from hidden layer as well as output layer. So okay, we still in let me remind you again, we still try to derive towards find the general step of our ANN models there. So means that when I give you this simple ANN model, okay, that is actually just to make sure that you can understand the basic mechanism, or the how actually how actually this backpropagation is executed in neural network. But our mission is still there. We want to find some a general step or this general algorithm, which actually later you will find that when you generalize everything, doesn't matter which architecture of ANN, you still can use the same algorithm to models or to develop the ANN. So in order to do that, we need to have some general step where actually if you change your ANN architecture, you still can use the algorithm or the studio code that you have modeled. So in the perspective of hand calculation, I think we already finished derive everything here. Means that if you have this kind of architecture, means that two neuron at the at the input layer, you have two nodes there, and then if you talk about hidden layer, you have two neuron. At the output layer, you have two. Then we managed to derive everything, which is important to prove that how actually the backpropagation works. Start from the forward pass to the backward pass. But let's say you want to change this model. For example, you want to have more neuron at the hidden layer. For example, not two. Let's say you have 3 or 4. So then, if you need to go back to the initial step where you need to derive again from at the beginning up until this part, or up until the backward pass part, so you can define each and every W and B that you have in the nodes there. Okay, so of course I want to show you a little bit how actually we still going towards to find a general step. Okay, so how to find a general step, train the ANN using backpropagation algorithms. Okay, again, this is the one that we already summarized in the previous lectures. This is the forward pass. Okay, and then this is a backward pass. Sorry, because I again during the previous lecture I make a mistake, draw everything in this slide. It should be, because this slide is say similar to the previous slide, so this one should be draw at the previous slide, but I have draw here. Okay, let me delete the drawings there. Okay, good. So okay, to make the algorithm, to generalize the algorithm or to find the general step where doesn't matter you change anything in your ANN architecture, you still can use the same algorithm. Again, you need to change a notation there, or the labeling process there, because when I use the labeling concept like this one, means that this one, the first circle I label as neuron number 1, this one is neuron number 2, this one is neuron number 3, this is neuron number 4. For if you label something like this, it's very difficult for you to generalize the algorithm. So instead of using this notation, I replace with another notation which is more generalized, which is this one. Okay, as you can see, what is the difference between this neuron and this picture and this picture is the label. So you can see there at the input layer you have two neuron. Of course, like I mentioned before, this neuron is not like the one that as similar to, is not similar as hidden layer and output layer, because hidden layer and output layer have actually inside the layer have the neuron. This one is not a neuron, it's just some dummy process where actually it's not consists of input function and activation function, because the x1 and x2 will go direct into this line and this line. So this one is, you don't have any process there. But just to make sure you have input layers, hidden layer and output layer, so you that's why each and every layer here you have consists of neurons. The one that only we have secured is only the neuron inside this layer, hidden layer and output layer. We don't care about this layer. input layer. So but again, instead of I labeling 1, 2, 3, 4, 5, 6, I label in this way, meaning that this one is neuron number 1 at the input layer, this is neuron number 2 at the input layer, this one is neuron number 1 at the hidden layer, this one is neuron 2 at the hidden layer. So same goes to the output layer, and then you can see that what is the difference. What are the other difference there? You find out that now instead of I'm using a W13 like this one, then I change it into W11, means that the interaction is between neuron number 1 here and neuron number 1 here, so that's why I call it W11. Okay, so again, if you talk about this W, is still the interaction is there between neuron number 1 at the previous layer and neuron number 1 at the current layer, which is at output layer. But to differentiate between W11 of this one and W11 of this one, I put a bracket there. So the brackets there will represent the number of layer. You can see that this one, why I put there as a 2, means that this W is belong to the second layer, which is this one. So this is the first layer 1, this is second layer 2, this is third layer 3. So that's why everything's that close to this one I label as 3, meaning that this W is going towards layer number 3. So the brackets there and the number inside the bracket represent the layer, the variables that related to that layer. So you can see that this one B1 at the layer 3, this one is B1 at the layer 2. So then you will know that if I talk about B1 as layer 2, meaning that is a bias at the layer, at the hidden layer, and because that is B1 is a neuron number 1, the bias at the neuron number 1. So that's how we change the notation. Okay, so again, we try to rewrite back all the hidden layer equation and output layer equation that represent the forward pass mechanism, consists of input function and activation function. So again, the brackets there represents the layer numbers there. So same goes to this one, which is the backward pass. Okay, in the previous one we label 1, 2, 3, 4, 5, 6, then I change the notation like that. So meaning that everything's belong to any variable belong to that neuron, then you know actually the brackets mean the number of layer, the layer number, and the variable at the below there represent the number, the neuron's number. For delta 1 means that is a delta belong to neuron number 1. When the bracket is inside the bracket you have 2, then means that delta is a delta at the neuron 1 at the second layer, which is the neuron number 1 at the hidden layer. So again, if you talk about all the expression that represent the backward pass, I just change it into these new labels. Okay, so let's try to make it more generalized. As you can see, at the output layer, okay, if you want to find E5, this is how you compute the E5. Remember how to define the E5? Yep, this one. E5 is equal to Y1 minus Y1 hit, negative at the outside there. So if you, I just multiply this minus 1 inside, so that's why this one become plus, so this one become negative. So this one is similar to actually Y1 hit minus Y1. So I just remove the negative, so that's why you can see that now it's Y1 hit minus Y1. So E6 is Y2 hit minus Y2. So from here, then if I change into new notation, it's look like this. Okay, means that error at the neuron 1 layer number 3 is equal to this one. Error neuron number 2 at the layer 3, which is the output layer, is equal to this one. So if I make this equation in form of matrix, it seems to be this one, which is this is the matrix represent this one. So if I want to represent this one as a vector, so it's look like this, meaning that each and every error, local error there happen at the output layer. Okay, output layer, because the bracket is 3, is equal to your vector of y head minus y1. So from here, this is y, this is y, sorry, this is y, and this is y head. So doesn't matter how many outputs there. So now it's become a vector or a matrix. So that's why I put a bolds there. The font is bold. So same goes to the delta. To find the delta, this is the old notation. If I replace it with new labeling there, you will find out that this delta 5 is actually a delta 1 at the third layer or at the output layer. So delta 6 is actually, now the new label is delta 2 at the output layer or third layer. So equal to your derivative of activation function, and now even the nets there I replace with the new labelings like that. So even the E I replace with this one. So if I convert this into a metric form, it seems to be this operation. And if I want to simplify this expression into a vector form like this, now it seems to be your delta of your third layer or the output layer is equal to your derivative function net of your last layer or third layer. And then that is actually why I use this small circle that is called as a Adamic Products. Okay, let me show you what is that symbols belong to, which is this one. Okay, it's called it Adamic Products, meaning that that's Adamic Products. If you have matrix A and matrix B, if you multiply by using this operation, I'm sorry, if I using this operation which is called Adamic product, is actually a element wise multiplication, means that if you want to find this point over here, this one multiply with this one, you get that one. If you want to get point over here, you must multiply this element and this element, then you get this element. So it's a multiplication, is a element wise multiplication operation, or is also known as Adamic products. So this symbol here is represent the Adamic products. So it should be a little bit don't confuse between this one and dot. Okay, the dot like this one is called a dot product between this matrix and this matrix, but this one is a Adamic product between F apostrophe and E here, means that element wise multiplication. So if you remember, if you want to implement this operation, okay, in programming, in MATLAB programming, so it seems to be, let's say if you want to do the operation of A and then Adamic product B, then if you want to run this one in MATLAB programming, then you need to do something like this. Yep. So you must put a dot, you must put a star there. So that means it's a element wise multiplication. But if you want to do a dot product like this, then you, let's say A dot B is just you A multiply with B. So this is the meaning, what is meaning by this one is a dot product. But if you want to do a element wise multiplication like this, that is in mathematics expression is represented by these circles. So that's why I'm using this representation. And then again you need to repeat. Okay, same goes to the hidden layers here. Okay, you can see that to find the E there, of course, like I mentioned before, the difference between the output layer and hidden layer is that the definition of E. Now this E here is expressed as this expression there, but for E5 and E6 to find if E5 or A6, then you need to express in this way. So that is the difference between output layer and hidden layer. So if you replace this expression with the new labeling, then you put it in the matrix there. If you convert into form of matrix, this is how it's look like. And at the end, this operation is a dot product between your W of your second layer and delta of your second layer. So you can see that because this one, if you talk about dot product, is this one multiply with this one, means that this one multiply with this one plus this one multiply this one, which is similar to this expression over here. So it's a dot product. And then to find the delta is delta 3 and delta 4 is similar to find to find the delta 5 and delta 6. You can see at the end this equation and this equation is similar, means that, like as mentioned before, doesn't matter is if you want to proceed output layer or hidden layer, the delta is definition is similar, means that you must multiply the integration of your activation function with your E. So at the hidden layer you do the similar things, means that you multiply between the F apostrophe and your E, but the difference is just this one and this one, because if you at the output layer, this is how we define the E. At the hidden layer, this is how you define your E. Okay, so from here you can see that this is the one that we can use after. Okay, again, just remind you why the mathematician put a lot of effort try to express any equation in vector like this one or in matrix like this one, is because they want to make sure that once you can generalize in this way, it's very easy for programmer to compute all these algorithms, meaning that because you have a many repetition process. So if you, instead of repeat the same things, if you can generalize into a vector like this, so you can code it, or you can make a code in one line where actually that operation can represent that multiple variable inside this thing. So that's why they put a lot of effort just to express this equation as a vector or as a matrix form like this, because once you find the equation in this a bold version like this, so it's easy for you to develop the general algorithm.